There exists an area so unfathomably large that we refer to it simply as space. And in that space we can explore and study fundamental questions about our place in the universe and our history of the solar system. We launch satellites into that space and utilize them to perform a host of vital functions, including communications, weather prediction, and much more. These systems are very complex and abnormalities do occur. However, they are not always as obvious as a dog floating around on the ship. Anomalies can take place and slow the connection, perform a task that does not complete, or shut the system down completely. Our team set off to study satellites in anomalous situations to help prevent possible disasters from occurring. We call our project the SED Testbed, short for the Satellite Anomaly Injection and Detection Testbed. We contracted this work for the AEROSPACE Corporation. We focused on the problem in which strange behaviors or anomalies occur on satellites, with a goal to understand and analyze those behaviors. The solution is to create software that will simulate an anomalous injection into the satellite and then detect said anomaly. We centered our attention around 5 anomalies: denial of service, a distributed denial of service protocol interrupting the satellite communications; runaway task, when there's a process that cannot close; memory leak, when the satellite is losing memory rapidly; single bit error, a switch in the bits of the satellite's memory; invalid command sequence, when the satellite attempts to execute a command out of order. But before we dive too deep, I would like to introduce the team that, despite an abnormal senior year, managed to stay positive and persevere. Together we have Matthew Gilligan, Vivian Nicholas Torres, Jerome Pineda, Aaron Tong, Alex Huang, myself Samantha Simpson, and Joshua Tran, who I will now pass the floor to.
At this time, I'd like to talk a little bit about Openstack Kit. As Samantha explained, OSK is a simulation system designed for users to test satellite commands and process sample telemetry. It is composed of several languages, including but not limited to C, C++, Java, Ruby, Python, and Makefile. Telemetry data refers to the information that is sent from the satellite to the ground network due to a request from the ground-side server or because it followed the pathway of the software bus naturally. The software bus is the system by which telemetry data is conveyed. This will be the primary mode on how we communicate our onboard or in-orbit anomalies. OSK is also composed of several systems, with each system acting as a different body of the satellite simulation. For example, our ground-side server will be controlled by Cosmos, which aids in the process of creating and executing commands, in addition to writing and activating our own scripts, which we can then push into the software bus. Our satellite systems will be controlled by core flight systems, which is naturally executed by memory bus processes, but also has manipulatable data we have access to, including onboard memory, onboard table memory, and housekeeping packets. These will be further expanded upon throughout our presentation as they are needed in each anomaly. I'd be remiss not to mention that a big use of OSK is the 42 flight simulations. This function gives users the ability to visualize their data with the telemetry data on their screen. Traditionally, this is a primary function of OSK, but we will not be using this process for our project due to the fact that often the anomalies we create would crash the system naturally, and it isn't feasible to visualize the anomaly and system when we wouldn't have access to it naturally. Hopefully, this provides a little bit more context on the development environment we worked in. For more information on how we approach the development of each of our anomalies, I'll hand it off to Aaron Tong.
Thank you, Joshua. Now that we have covered a high-level overview of the various software included in Openstack Kit, I will now cover how we plan to use it to create our anomalies. First, when we began to look into how core flight system applications functioned, we immediately noticed that there were functions that easily allowed core flight system applications to send and receive messages on the software bus, which is how the applications communicate with each other. Upon finding that out, we also saw a framework in Openstack Kit for creating a core flight system application that we could expand upon. This framework would help create an application that is the equivalent of a Hello World app for the core flight system, which is helpful because it served as the foundation of our understanding of core flight system applications. The application created by the framework also served as a starting point for all of our core flight system applications. Additionally, while looking for documentation on specific core flight system applications already included in Openstack Kit, we discovered functions such as the peek and poke functions in the memory management application. After looking at these two functions, we realized they could be used to implement our single-bit error anomaly. Similar instances also occurred for our other anomalies, and we shared any findings during our weekly meetings together. Additionally, Cosmos was helpful because it provided a simple UI that would easily allow us to send single commands from the ground side through the Command Center module. Cosmos also provided other modules that were useful, such as Script Runner, that allowed us to run Ruby scripts that could execute a sequence of commands. This module was used in our first proof of concept demo for the anomaly, Denial of Service, or DOS. Although we thought we could quickly implement all of our anomalies while looking at the provided API, it proved challenging because of certain system limits in Openstack Kit that created roadblocks for our team. These roadblocks and challenges that we face while implementing each of the specific anomalies will be expanded upon when we talk about each of the anomalies. Thank you. I will now pass the floor to Vivian.
Thank you, Aaron and Joshua. Denial of service occurs when network communication services are interrupted or shut down, making them inaccessible to the intended users. This is often an attack carried out by hackers who aim to overwhelm the network with more traffic than it can handle. So a network intended to transfer incoming and outgoing data and requests is being flooded with fake ones. The motive behind these attacks can range from simply disrupting service to even extortion, for example, business competitions, or requesting the service owner to pay a ransom for the hackers to stop the attack. Our goal is to simulate a denial of service by injecting the flood attack on the Cosmos CFS network and develop a program that will continuously monitor the network traffic. Once an increase in traffic is detected, it will notify the user. We have implemented this anomaly both as ground and satellite based. However, to better control our injection and detection, we will present this anomaly as satellite based, meaning we will be executing the injection and detection through the core flight system. Our approach was to create two CFS applications, the Denial of Service Injection app and the Denial of Service Detection app, both responsible for injection and detection respectively. We use a toolbox called Netwalks to help us carry out the flooding attack. Once we execute the injection command through the injection app, it will start spamming the network with data packets. For detection, we execute the command through the detection app, which will begin monitoring the network traffic. We do this by continuously checking the system's RX bytes file. This file indicates the volume of data packets received. We then calculate the rate in kilobytes per second. When this rate exceeds a certain rate, the app will send a message to the CFS terminal and notify us of any unusual amount of traffic. Overall, the goal of simulating this anomaly is to help detect a flooding attack to the network as soon as possible and execute a solution before the attack causes any serious damage. Thank you. I will now pass the floor to Nicholas to talk about Runaway task.
Thank you, Vivian. Hello all, and welcome to my presentation of the Runaway task anomaly of the said testbed. In this presentation, I will provide a brief and general overview of the Runaway task anomaly. The Runaway task is designated to simulate a rogue subroutine that may appear within the satellite's flight software. This anomaly may represent several issues within the software, including but not limited to computationally intensive tasks and unresponsive apps aboard core flight systems. The runaway task can span for any CFS app that slows the system. The question remains how a runaway task may appear in the first place. To answer this question, we look at two chief factors, namely program vulnerabilities and the environment. As many programmers know, accounting for the defending against errors and bugs in a program is quite the task, only increasing in difficulty as the software grows. Occasionally, a programmer may not catch an error in the program's logic, which may cause issues for the software in the future. Such errors may cause a runaway task that the software will need to see and report. Additionally, the satellite may find itself amid harmful electromagnetic radiation, which may corrupt the flash memory containing the machine's code instructions for the satellite's processor. Such an event may also cause the system subroutine to behave abnormally. Next, I will explain how the injection of this anomaly was implemented aboard CFS. To simulate an unresponsive CFS app, I created an example with a particular runaway task command. This command directs the app to ignore both user input and system input. Under the hood, my example app will no longer update its execution or command counters, and does not process incoming requests by the software bus. As far as the system is concerned, the example app has become a runaway. On the detection side of the process, the built-in health and safety application catches any app that fails to execute as expected by the CFS. For this, the healthy and safe application is designed to monitor the execution of the example app. If health and safety detect that the example app has failed to execute, it will print a message to the user. Health and safety may be configured to take different actions upon execution failure. This printed message will show that the detection is working properly within the application. In the case of an actual satellite, the restart option may be the best option for a runaway task. This concludes our discussion on the runaway task. I will now pass the floor to Alex Huang.
Thank you, Nicholas. Hello, I am Alex Huang, and I will be talking about the anomaly memory leak. A memory leak occurs when data is not being appropriately deallocated and released to the memory, resulting in overall reduced available memory for the rest of the platform to operate on. As more and more blockage occurs from this anomaly, performance degradation will appear across all systems operating on the platform. This primarily happens on software expected to run long-term without resetting or shutting down, which is expected for satellites operating in deep space. The intended goal for this injection is to help simulate what occurs on a satellite. More and more of its memory is allocated but not deallocated properly over time to observe how the satellite responds and how it manages performance issues given its loss of memory assets. From there, we were to design a means of detecting the memory leak as it occurred on the satellite so that the ground team could be alerted to the emerging problem on the satellite. We have not successfully created an injection for the anomaly, but have highlighted key points on implementing such injections on the satellite simulation in the future. We discovered some points on attempting to create a memory leak because the satellite by design does not accept dynamic allocation, so any attempt at occupying memory must be static in nature. In addition, the memory allocation is highly unstable for the satellite, and suddenly settling or altering large sections of memory outside of its design can cause system crashes, which would render the injection to be ineffectual for observation. The recommendation is an in-depth analysis of how the satellite handles memory allocation, in addition to researching how to avoid crashing the satellite via system error from the injection is a must. Memory addressing needs to be learned before attempting the injection, especially for identifying what range of memory can be safely occupied for at least a proof of concept model. A more in-depth understanding of the built-in Memory Manager API and perhaps the CFE mempool functions would help create a more feasible and stable model for injection. That concludes the discussion on memory leak. I will now pass on the floor to Jerome.
Thank you, Alex. Hello, my name is Jerome Pineda. I will be presenting the single-bit error anomaly. Now, what is a single-bit error? A single-bit error is an anomaly that happens within the memory. Within the memory, data is stored in a sequence of ones and zeros. These ones and zeros are called bits. When a single bit error occurs, one of the bit is flipped from 1 to 0 or 0 to 1. In order to illustrate this, here's an example. Let's say we have an 8-bit sequence, or what we like to call a byte. Within that byte, we have the bits set as 10, 10, 10, 10. Let's say we want to target the third bit in this sequence to be flipped. So now, instead of the original sequence, which was 10, 10, 10, 10, we now have the new sequence 10, 0, 0, 10, 10. This is the basic concept of single bit error. The only big difference is that instead of just targeting that third bit, we're going to be targeting any random bit within the memory. Now, in order to replicate this anomaly within our system, we needed two things. First, an app that can be considered the quote-unquote rewritable memory of the satellite, and a command that will actually do the single bit error injection. So we just did that. We created a dummy application called SBEI, or single bit error injection for short, and then we also created the command that will do the injection itself. So for the injection itself, we decided to aim for 8 bits of the RAM, or a byte of the RAM, within the dummy application. So now, whenever the command for the injection is called, one of the bits of that byte within the RAM is now flipped. Now, onto detection. As of right now, detection is still a work in progress. Conceptually, however, our plan was to utilize the function within the satellite called checksum. Within the documentation, it states that checksum can check the state of the memory. It does this by creating a snapshot of the memory. Then, once any kind of new state of memory is developing, it will compare that snapshotted state of the memory to the new state of memory. Overall, we were able to accomplish the single bit error injection prototype, and now we have the documentation on how to move forward with the detection. That concludes our discussion on single bit errors. I will now pass the floor to Alexander Lopez.
The last anomaly that the testbed analyzed through are the invalid command sequence anomalies. This occurs when a satellite is not performing the commands in the correct behavior due to having mixed up the sequence or order, hence the name. Sometimes this is caused by the ground system not executing commands properly. Other times, external threats can mess up the sequence. We aim to detect and eliminate the anomaly in the satellite systems because sometimes even the smallest changes to the command orders might affect the system very heavily. Initially, looking to the housekeeping packets was the main goal, but that caused some issues, leading to another method I will explain. The primary way of detecting these invalid sequences involves looking to the Cosmos directory of the command logs. By converting them into text files and generating arrays from them, allows the history of the command that would have been executed to be easily read. At this point, the command detects any unusual completed command orders. Detection mainly consists of comparing the current command history with hard-coded examples of valid command sequences. If seen, the program would have to notify the user about this. An example was created in the form of a basic application. This app contains 4 commands that must be executed in a specific order. So if the detection methods right now can detect if the completed order is a valid sequence or not. This is performed with a hard-coded array showing what the correct sequence should look like when executed. With this prototype implemented, other instances of invalid command sequences should follow this example to catch any unusual command sequences that the satellite system accidentally allows. Thank you. I will now pass the floor for Matthew to conclude.
Any of these 5 anomalies presented today can occur on the real satellites currently in orbit, either by malicious intervention, user error, or random logical errors caused by natural forces such as solar radiation. These anomalies can stop the satellite from performing its duty, cause it to lose connection with the ground system, or even cause physical, sometimes irreparable damage. Once a satellite is in orbit, it's there for good. If there was an issue with its manufacturing, or if it was damaged while in orbit, it cannot be fixed. That's what makes anomalies so devastating. If something happens to stop the satellite from performing its duty, or cause it to lose connection with the ground system, there's nothing we can do about it. That is what makes our project so important. OSK provides us a safe space to test and study satellites. By creating a system where we can simulate anomalies and detect those simulated anomalies, we can better understand these issues and apply that understanding to real satellites and correct anomalies before they cause damage. Unfortunately, we were not fully able to implement all 5 of the anomalies. However, on the ones that we were not able to finish, we have created detailed documentation of what we have attempted, what caused those attempts to not work, and a roadmap of ways to implement them in the future. Also, as you can imagine, there are more than 5 anomalies that can occur on a satellite. There are hundreds of issues that can arise on these sophisticated pieces of technology. We chose to implement these 5 anomalies in particular because they are amongst the most basic anomalies that can occur. Future projects can use these fundamental anomalies to expand on our work and implement ways to inject and detect even more anomalies in the future. In closing, let's think back to that dog in space. There were many times where we felt similarly out of place while tackling this project. However, our liaisons at the AEROSPACE Corporation, Rick Johnson, Denny Lee, KARINA Martinez, Pablo SETTECASE, and Andre Chen, played a unique role in supporting the team, and for that we are incredibly thankful. We would also like to thank David, who was one of the developers of OSK, who graciously allowed us to consult him with any issues we ran into while developing this project. And a special thank you goes to our advisor, Dr. Abbott, who is always willing to make himself available for the team. This project was an incredible opportunity, and we are incredibly grateful. Lastly, thank you to the Computer Science Department at Cal CLA for all of your dedication, and to everyone who tuned into this presentation. We hope our project provided you with a deeper understanding of all the challenges faced in maintaining satellites.